Welcome back, and I've got another brilliant experiment to show you today, and one I've been meaning to show you for a long time. This one goes under the rather unusual name of Faraday's ice pail experiment. So this experiment was one that was done by the absolute genius Michael Faraday in about 1843. And it's called the ice pail experiment because what he used was a bucket to carry ice in. I'm sure you've got them at home if you are great champagne drinkers. It's those buckets that have loads of ice and a bottle of wine in them. But back in the day, it was called an ice pail because it looked like, pail of milk, that kind of pail. So this experiment got the name the ice pail experiment. So let's see what we have to do to make it work and what it explains about the nature of charge in closed conductors. So again, this is an experiment that's sort of in the back of the cupboard, and I've never really seen anyone else do it before, but it's worth showing to you. The apparatus is very simple. What I've got here is a gold leaf electroscope that shows whether charge is present on this system, and I've got a link to that if you don't remember how the gold leaf electroscope works. On top, I've got my little ice pail, my little bucket. It's not really big enough for a bottle of wine and some ice, but you get the idea, and that connects to the electroscope. And then here, I've got a little system that allows me to put charge on these metal discs. I think Faraday used an isolated, insulated metal ball, but it won't make any difference. So let's get started. So the first thing I'm going to do is put a little bit of charge on this electroscope. So I've got a little metal ball or little metal disc here, and I'll charge it up. I won't explain this system. I'll do that in another video. Touch it on there, and the gold leaf rises ever so slightly. I'll zoom in on that in a minute. Okay, the next thing I'm going to do is charge up this large one and put it inside the ice pail, the container, but I'm not going to touch the walls of the container, and let's see what happens. So, a bit of a close-up. Here's the small disc, just putting a little bit of charge on the electroscope. So let's charge up this metal disc now and put it inside the ice pail and see what happens. So you'll notice as I put it in, the leaf rises quite a bit further. If I take it out, it goes down. Again, I'll zoom in. And if I put it inside and move it around, it doesn't really change its position at all. The leaf doesn't move from where it was, but it always drops when I take it away. But what I'm going to do now is take the metal disc and touch it onto the walls of the ice pail, and I think you'll be surprised by what happens. Okay, so here we go. Here's our charged up metal disc. In it goes. You see the leaf rise, and then I'm going to touch it on the walls of the container, and not a lot happens. The leaf stays pretty much where it was, but here's the interesting bit. If I take it out, there's almost no change at all. And if I now put this on another device that measures charge, it will find that this is neutral, which is really surprising. So why hasn't the electroscope changed its reading and yet it's stolen charge from this one? That's going to take quite a bit of explaining. Okay, I said I'd prove to you that this was neutral once it had touched the can. So we'll just get the leaf to rise again. There we go. Touch the can and there's almost no difference. Take this out, and I'm saying this is neutral now, so I'll discharge the electroscope and touch this onto the metal of the electroscope, and you can see that this is completely neutral. So it must have been charged to cause the leaf to move, but now it has no charge on it at all. And the critical step that you need to remember is that when I put this in, the leaf rose, but when I touched the sides, didn't really rise much more, and when I took it out, it didn't seem to make any difference to the position of the leaf, but the disc is now neutral. So I've zoomed in a little bit. Here's the small disc, just putting a little bit of charge on the electroscope. And now for the larger disc, there we go, in it goes, the leaf goes up. the leaf goes down, the leaf goes up, move it around inside, the leaf stays where it is. Touch the side of the can, makes no difference. And finally, prove that the large disc is neutral. Good, so now for the tricky bit, trying to explain this. And I'll cut to the chase. Faraday produced this experiment to show that there can be no net, no overall charge inside a closed conductor. Now, I know you're saying, well, that's not closed, it hasn't got a lid on it. But basically, when we're deep inside this, we can consider it to be completely closed. And it's a bit confusing because you think, well, hang on, the leaf rose, so there must be some charge in there. But I need to show you now why there was no overall charge inside the ice pail, inside the closed conductor. So here we go with an explanation. So we'll charge up this little disc and put a little bit of charge on the electroscope, and I'm making this positive. So if I've made this positive and I touch all the metalwork of the electroscope, then I attract electrons, free electrons from the metal system onto this disc, and so we've removed electrons from the electroscope, leaving the leaf and the ice pail all positive. Okay, but what we're going to do now is we're going to charge up the larger one. We're going to charge that up positive as well. It's going to charge up a bit more positive because there's a bigger surface area, and we're going to explain what happens when we put that in before we touch the metal can. Right, so now let's charge up the bigger disc, so that'll be positive as well. And if you remember, if I put that in, the leaf rises, and I take it out and the leaf falls down. And if you know a little bit about charging by induction, when I put this in, electrons will be attracted to this positive metal disc but won't be able to reach it. There's an air gap between the can, the ice pail, and the disc. So we've got a positive metal disc attracting electrons up to the can and getting as close as they can to this, which will be the inside edge of the ice pail. So electrons will appear on the inside edge. Now, I hear you saying, well, isn't the whole purpose of this experiment to explain that you can't have charge on a closed conductor? But there's something else going on that we need to explain as well. So when we brought the large metal disc in and we noticed that the leaf rose, we know now that that's because of charging by induction. Electrons are attracted up and they end up on the inside of the can. But here's the clever bit. We did say you can't have any charge overall in a closed conductor. But remember, the electrons are on the inside of the can, and this is positive. And it's the positive nature of this that has attracted those electrons. So if you think about it, this is as positive as the electrons are negative on the inside of the can. So there's as much charge on this as there is on the inside of the can. So now what we're going to do is explain why when we touch the metal can, this becomes neutral, but the position of the leaf doesn't change at all. Good, so for the final bit of the explanation, you now know that the negative charge that has been induced on here by putting the metal disc in that was positive has made the gold leaf electroscope more positive, but the negative charge on the inside is the same as the positive charge on the disc. So there we go, there's no overall charge inside the closed conductor. So if we touch the metal disc onto the metal can when it's all correctly charged up, those electrons jump from the metal can onto the disc and neutralize it. So we've got no charge at all inside the can, but the positive charge on the outside still remains. So just to summarize that last bit, if you remember, this was positive, the inside of the can was negative, so there was never any overall charge inside the can at all, so it couldn't have affected the position of the leaf, and when we touch, doesn't make any difference to the leaf position because it was neutral in total inside the can all of the time. And just before I forget, this being neutral when it's touched the can and taken out proves that the charge that was on the inside of the can must be exactly equal to the charge that was on this metal disc because it's completely neutralised it. So I hope you enjoyed Faraday's ice pail experiment. I've spent quite a bit of time trying to work out how to explain it because it's very easy to demonstrate but not so easy to explain to students. Anyway, I'll be doing another video soon and I look forward to seeing you then.